Hello, today I will talk about the organometallic chemistry, and this will be an introduction course. And what is the organometallic chemistry? It's a very interesting part of the chemistry, I think, and this is the book that I will follow. And what we are looking in organometallic chemistry is that we are looking at the compounds containing both sigma and pi bonds, but these are the metal complexes generally, and they can make very interesting uh, compounds. And we will also look at the different compounds. For instance, we look at the cluster compounds, and we also look at the molecules containing carbon fragments that are unusual or unknown in organic chemistry. And the most beautiful example is hemoglobin. I think hemoglobin have both organic part and the metal part. So this metallic part makes a complex. So it makes a hemoglobin iron complex, and this is the area of the organometallic chemistry. And then we will also look at the sandwich compounds, and I will put a beautiful picture of a sandwich compound here. So what's happening is that, for instance, what is the organometallic chemistry? We can think cobalt Cl2, which is a very common compound, and we can dissolve it in water, right? And what we expect is that it becomes copper 2 plus 2 Cl minus. The idea, actually, this is correct, but there is also a complex formation. Instead of this, we observe a compound, which is this one. It's a very interesting compound, and this compound have an octahedral structure, which I will draw here. So we have an octahedral geometry for this compound. It makes bonds with water molecules, and this is a complex metal compound, and all the complex have 2 plus charges. As you know, the water molecule is a ligand, and it's a natural ligand, so that the cobalt here is in +2 oxidation state. And which is more stable? For instance, cobalt in water. So we think that water or cobalt 2 plus in space is more stable. So the answer is water. In water it becomes more stable due to this complex formation. And to understand why it is more stable, we should know that molecular orbital theory. I will show some molecular orbital theory structures, and to draw the molecular orbital, actually knowing a group theory is also essential. Chemical application of group theory, and there is a book, actually I will put into the name of the book. And then we need to know LGO also. And for the next 2 lectures I will construct some molecular orbital geometry. So here we have covalent bonds, right? We have covalent bonds, and generally these complexes follows the 18 electron rule. I will talk about it in the next a few lectures probably. But the 18 electron rule have some exceptions. It's not always valid. And so many organometallic chemistry and their reactions are actually depend on the 18 electron rule. And we can also look at the different system, for instance, the 6 system, the 8 systems, and the 10 system for the complexes. And for instance, the 8 system has square planar. And for instance, there is a effect of the legend here. What is the legend? For instance, we can think a legend, a carbonyl legend. For instance, we have CO legend or those cyan minus legend, right? And I will always give some examples. For instance, nickel CO4 complex, and we have also nickel cyan4 2 minus complex. So again, nickel in here, for instance, in 2 plus oxidation state, and carbonyl is neutral ligand, so that nickel is metallic here, so it is in the 0 oxidation state. How can we predict the geometry of the compound? So for instance, in here, this is a this is a D8 system, and it has square planar structure. What is the structure? So we have a nickel atom, we have 4 ligands, and we have cyan ligands here. So this is the structure of this compound. In here, it has a tetrahedral geometry, like CH4. So if I want to draw it, we have a nickel here, so one of the CO group comes here, comes us, and the other is goes back, and we have 2 CO on the paper. So this is the tetrahedral geometry of the compound. And what's happening here? For instance, we will look at the properties of the ligands. For instance, CO binds to metals with low oxidation states, and cyan is different, and it has a minus charge, and it prefer to bind metal with high oxidation state. And the oxidation state of the metals are very important to determine the geometry. And by the way, some ligands, for instance, vanadium, it's a very interesting compound, I guess. It's an early transition metal, and it can take negative oxidation state. One of the example is vanadium CO5 minus 1, and this compound vanadium have minus 1 charge. It's very interesting, and we will talk about some reaction and reaction mechanisms, and we will predict the geometry. I want to write it. We will talk about the reaction mechanisms. What mechanisms? Firstly, we have addition and elimination reactions. So these are the important reactions. We have also insertion And these reactions are important for the catalytic properties. So there is a catalytic cycles. I want to also write it. We will look at the catalytic cycles and some mechanisms of these catalytic cycles. And I will put a picture here for the catalytic cycle. Oh, I don't have to. So we have a, for instance, catalytic cycle here. We have a catalytic cycle here. So this compound becomes this one. So there's a CO leaves here, for instance, and there is another reaction in the B step, and we will look at this kind of reaction mechanisms. And this organometallic chemistry is actually common in some fields of the chemistry. For instance, in organic chemistry, right? So there is a very common reaction, which is the granite reaction. So it is actually an organometallic reactions. What is this? Granite. We have a different, a very interesting molecule, magnesium compound, and they can react with an aldehyde, for instance. And this bond can react with this one. Another bond goes to the oxygen side. So we can create this kind of form, molecule. So there is a carbon atom and there is R group here. And if you put it water and little bit of acid, for instance, then we can make this kind of compound. Actually, this is an important molecule, and this is actually organometallic chemistry reaction. And the other example that I gave you before, hemoglobin and iron complex. Hemoglobin is very different molecule, very interesting, and it makes a bond with oxygen, and it can also make a stronger bond with CO. CO is a strong field agent, by the way, and it binds to the hemoglobin stronger than the oxygen, and therefore there is a CO poisoning. And this is a life of the organometallic chemistry. And who is the father of the organometallic chemistry? Alfred Werner. And who took the Nobel Prize in 1907. So this guy was a German guy, and if you are curious about the history, you can also look at the guy. And what you should know, I want to say is that who should take or watch this course. Firstly, you need to know at least the basics of the MO theory. And if you know the group theory, it is very good. So you need to know the theory of bonds. Okay, so it's important. I think you should familiar the SN2 SN1 reaction at least, and E1 and E2 elimination reactions from the organic chemistry. But you don't have to know all the organic chemistry reactions. It's not essential for this course at least. And what you should know, at least you have a good inorganic chemistry knowledge. And if you know these topics, then you can watch the other videos. And that's all for this video. Thank you for your attention. And if you have questions, you can write a comment. If you make a comment, I can answer it, and it might be beneficial for me. It will be a feedback for me also. And thank you.